In general, the basis vectors that we have defined now are not going to be constant. They are going to be vector fields that depend on the position we are in. In particular, this means that in general, the partial derivatives of the basis vector fields with respect to the coordinates chi is not going to be equal to 0, signifying that the basis vector depends on the coordinate chi. We can see this, for example, in the result of the exercise that we have just done, where we found the basis vectors in polar coordinates. And we found then that the different basis vectors depended on the point where we were looking. However, it should be noted that these partial derivatives still define a vector field. And as such, we can expand this vector field in terms of the basis vectors themselves. So if we expand this vector field in terms of the basis vector EC, we find that it is equal to some component gamma c, which is going to depend also on a and b, multiplied by the basis vectors EC. And we call these components gamma ABC the Christoffel symbols of the coordinate system. To get a graphical interpretation of the Christoffel symbols, let us consider the tangent vector field EB at one point and at a different point, with a difference vector of epsilon times EA. As we said, EB at these different points are generally not going to be the same vectors. If we move the vector EB from the second point to the first, we will see that there is a difference to the tangent vector EB at the first point. And we can draw this vector, which is going to be, to linear approximation, epsilon times the partial derivative with respect to chi of the tangent vector field EB. The Christoffel symbol gamma ABC is then the component in the EC direction of the change in the EA direction of the field defining the EB direction. So, in other words, it's going to be the EC component of this green vector that we have just drawn as the difference vector between the EBs at different points, separated by epsilon times EA. It should be noted that we can compute the Christoffel symbols as follows. If we take the inner product between the dual basis vector EC with the partial derivative in the chi direction of EB, then we can use the Christoffel symbol definition to write this as the dual vector EC inner product with gamma ABD times ED. Now using that the inner product between a dual basis vector and a tangent basis vector is the Kronecker delta, we find that this is equal to gamma ABD times delta CD, which is equal to gamma ABC. The argument that we have just presented can also be done for the dual basis vectors, which also generally depend on the position. So we look at the partial derivative in the A direction of the dual basis vector EB, which should be equal to some component C ADB multiplied by the dual basis vector ED. However, these components C can be related to the Christoffel symbols. If we take the inner product between the dual basis vector EB and the tangent basis vector EA, we know that this should be equal to the Kronecker delta BA. Taking the derivative in the C direction of this, we find that this is equal to 0 because the Kronecker delta components are constants, either 1 or 0. We can also use the product rule for derivatives to write the original expression as dc EB scalar product with EA plus EB scalar product with dc EA. The first of those terms, by definition of the coefficients C, is equal to EA times C CdB multiplied by ED, and the second we have seen is equal to the Christoffel symbol gamma CAB. Again, we use the fact that the inner product between a dual basis vector and a tangent basis vector is a Kronecker delta to rewrite this as C CAB plus gamma CAB. And since this should be equal to 0, it directly implies that C CAB must be equal to minus the Christoffel symbol gamma CAB. Or in other words, the partial derivative in the A direction of the dual basis vector EB is equal to minus gamma ACB multiplied by the dual basis vector EC.